okay. So I think let's we introduce first before we start our your talk, Dr. Saiful. So silakan, very good
Okay.
afternoon. So thank
Okay.
you very much for those who joined today. Maybe uh, what the others maybe join after this. So thank you very much to Dr. Saiful, bin Dr. Azmi bin Haji Husain from City Darussalam, right? And agreed to give special talk today. So let me briefly introduce our speaker. Dr. Saiful bin Haji Husin is currently a senior assistant professor at Mathematical Science Department, Faculty of Science, University Brunei Darussalam, which is Brunei Darussalam. He obtained his Bachelor of Science Education. Oh, cikgu lah, isn't it?
Yes.
Cikgu eh?
Yes.
Okay,
Before this, I was a teacher,
okay. Now,
secondary school teacher. Yeah.
okay. From UBD, then Master San, University of East Anglia, UK, and PhD in Mathematical Science from Australian National University and AU in Canberra, Australia. He had many years of experience using mathematical software for teaching and research activities. His research interests include mathematical modeling and simulation in the area of material sciences, climate change, and agriculture. His research experience as former UBD FM technical coordinator and former deputy director of UBD IBM Center, collaboratively working with researchers at IBM India, IBM Watson, New York, and Texas, USA, and IBM Brazil on cutting-edge smarter planet modeling topics on regional climate weather modeling, renewable energy, and forecasting using high-performance computing facilities at UBD. Had resulted in some high-quality top-tier publication of several joint patents of potential commercial value. Okay, that's briefing about Dr. Samsul. Actually, I know Dr. Samsul since 2019 lah, Dr. Saiful lah. We met in KL during that time.
Yes. That is actually when I supposed to go to your place at UTP
Yeah,
uh
yeah, yeah.
with Professor Anwar Osman.
Yeah, correct. Yeah.
Yes. Mhm.
So, okay, I think without further ado, so let's we invite Dr. Saiful Azmi Bahaji Usin to present his talk. Okay, Dr. Saiful, over to you now.
Okay, thank you. So I just share this one.
Yeah, share screen lah.
Okay. Can you see my screen?
It is
Hello.
loading, so we need to wait
Oh, it's
maybe a few
loading.
seconds.
Okay.
It's loading. Yeah, we wait
Yeah.
first. Yeah, your boss is here, Dr. Elvina.
Yes. Dr. Albina is here. Yeah. Can you already see the screen?
Okay, it's still loading, so
Oh,
we
okay.
wait a moment lah. It's still loading now. Still loading. It's empty here. Just showing
Just
block
can I
diagram.
stop and then okay, I stop while and I share
Okay,
again.
then share again. Possible.
Is it still?
Yeah, still starting to share content.
Okay.
Okay, so alternatively, Dr. Saiful send to my WhatsApp lah, your slide,
Ah,
then I share
oh,
from here. Asal possible lah.
okay. Uh,
Send to my WhatsApp, then I share screen here lah, then you can present lah. I become your assistant today, no worry. Okay.
okay, let me. Can I send you to email?
Also possible? Yeah, yeah.
Uh,
Send to my email, then I just share lah.
okay, maybe it's a. Sekejap ah. I'm
Okay,
opening
yeah.
my email.
Ya, boleh, 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 boleh.
Uh, already sent.
Okay, wait. Wait. Let me load it first.
So I just stop this sharing now.
Yeah, yeah, wait.
Uh,
Wait. Okay, let me share screen.
uh, ways to stop.
Just stop sharing lah.
Okay, stop. Please say stop video. Strange ah, kenapa dia? Oh
Stop
yeah, yeah.
sharing,
Sorry,
stop
sorry,
sharing.
sorry. Okay,
Dia ada
sudah.
stop sharing. Dia ada
Okay, already
button.
done.
Okay, sekejap.
Okay, done.
Dah kan?
Yeah.
Okay, let me loading first your presentation. Okay, so let me share screen now. Yeah. Okay,
Yeah.
okay. Okay, so my apology for the technical issue. So now
All right. Thank
we
you.
invite once again Dr. Saiful Azmi Husain, Senior Assistant Professor from UBD, to present his talk modeling the COVID-19 pandemic for a small population size. How far is the prediction from reality? Yeah, Dr. Saiful, over to you now.
Okay. Thank you, Dr. Samsul. Okay. Assalamualaikum warahmatullahi wabarakatuh and good afternoon. By the way, before I start, I would like to extend my sincere thanks to Universiti Malaysia Sabah for allowing me to be the invited speaker for the FKI Public Lecture Series, Volume 3 for this year. So my topic is, the title of my talk is Modeling the COVID-19 Pandemic for Small Population Size. And we want to know how far is the prediction from the reality. Actually, this is my joint work with one of our final year project student and with my mathematics colleague. This is in when the COVID-19 started in 2020. So the summary of my talk will be the motivations, the overview of this COVID-19 research study, and the mathematical model that we use to predict the outcomes, and I'll present the results and discussions, and finally I'll present the conclusions and the recommendation for further research. The motivation is as probably in Malaysia, I think they have I'm not sure they have the excuse me, the app that can actually monitor an epidemic outbreak in Malaysia. In Brunei, we have Bruhel. We call it Bruhel app. Um, every Bruneian should have download this Bruhel help app in their mobile phones. It's actually make them easier for to see if how many cases had been actually recorded during that time, in 2020, uh, as well as other personal health records. This one, it's we call it a personal digital health, personal assistant digital health, not only to look into the epidemic monitoring, um, in terms of looking into the recorded cases, but also our historical medical record, what sort of drugs that we're taking, cases, I mean our own medical cases, is also inside this BruHealth app. And the other motivation is if we want to provide accurate prediction as much as we can for the policymakers. So the model that we use maybe can help the policymakers to make some decision in the future. So just want to recap back what is the overview of our COVID-19 research study is the historical facts. As we know that in 2020, the world is facing the coronavirus pandemic. The COVID-19, which is, we call it coronavirus disease, 2019 is a new type of virus which cause pneumonia and organ failure or even death, because first of all, they will attack they started with the sore throat, okay, and then upper respiratory tract. So this way they actually the virus target the upper respiratory tract, and they will go down to the lungs where they actually cause less oxygen, and then this will affect the breathing for human so it causes uh, difficulty for the patient to breathe, and it will eventually cause them. It will eventually cause. I mean, critical. I mean, if they are not they are not actually critically being what do you call it, managed. It will cause that. Of course, in Brunei, at that time, it's very alarming because we don't know this, as we know that the virus was only first discovered in Wuhan, China, in late December 2019, and it's very fast spreading within 2 months globally. Okay, so on March 11, 2020, World Health Organization declared COVID-19 infection as a first wave pandemic. So, and unfortunately, at that time, vaccines are not yet developed. So, the only way to prevent the virus is from spreading faster is to control the spread by doing a lot of steps. I think, as we know that in Brunei, we have this SOP and movement control order. Maybe in Malaysia also they have PKP as well. Um, and of course, they will come to us. They are locking down even the country itself for some worst country which they declare emergency. Okay, so as of course the schools will also be closed at the time, and we have to wear masks and social distancing, washing hands frequently, and so on. So just to let you know that since the study is about Brunei, so Brunei Darussalam has a finite population of nearly half a million. That is in 2021 census. Um, so I'm not sure now how much. I think there's about few percentage growth in terms of population, but of course Brunei is still almost half a million until now probably. But of course, even in small country like Brunei, the first case was detected on March 9, 2020. So this is very alarming because we heard with the media and so on, we heard that these cases have been spreading around the world. In just 1 month, the total cases in Brunei already reached 136 total cases. That include imported cases as well. So the main objective of our research study is to use a common and suitable epidemic model to predict whether or not the progression of COVID-19 pandemic for a small population size is effective or not. So we look into the case scenarios of the models in terms of the spread of the disease by taking prevention case from the government's strict rules and regulation. Next.
Okay.
Okay. So the um, the mathematical model, common model that people use, most mathematical modelers use is the um, McKendrick uh, SIR epidemic model. SIR is S stand for susceptible, I for infected or infectives, and R for uh, recovered, or sometimes in this case for we use remove, because remove can be mean recovered, people who are recovered, or deceased, or people who died. So this SIR model is a quite simple model. This has been used uh, to look into the human to human transmission, and which describe the flow of individuals through the three mutually exclusive stages of infection, susceptible, infected, and removed. Okay. So, and we know that in sorry, I have can we go to the, yeah, there's this infection rate is given by some number here, alpha times this susceptible times I. Okay, that is the infection rate. How much is the infection rate for that particular spread of the disease? And there's another one from I to R. There's a recovery rate. How fast is the recovery rate? Beta multiplied by the I. Okay, so that is the model that we use to predict the disease. Okay, thank you. Can we the next one? Yeah, thank you. So the terminology is, before I start talking about what is I, so S of T is the fraction that is susceptible to an infection disease. So people who are bound to get infected, so is given by S at some time T. I is the fraction of those people who were infected at that time. R is the fraction that people who are recovered at that time, or maybe recovered, or people who can't make it, who pass away. And S naught is the initial number of susceptible. I naught is the initial number of infected. and the R naught is the initial number of recovered. Not that R naught is R of 0 is not R naught. R naught is the basic reproduction number. So this is also a measure which how fast is the disease is being transferred. So in other words, it is the average number of people that will be infected by one person throughout the infectious period. Okay. So in the model, we need assumption as well. As we know that without assumption, the model will not going to be correct. So first, we need to assume that the population or susceptible must be a fixed number. So mean is a constant. Okay. So birth rate and death rate must be ignored, because if not, then there will be a changes in the total number of population. No immigration, no people going inside and people going out. So this is the assumption. And the rate of infection must be constant. The rate of recovery must be constant. The disease and recovered people must be put as removed category, and those survived can be assumed immune to the virus. So those people who have been infected and survived from this coronavirus, COVID, they are assumed to be immune to the virus. So the total size of the host population remain a constant, which is given by capital N, which is just the sum of susceptible number of susceptible, those susceptible, uh, plus the infected and plus the recovery. Okay. So of course, if you look into the mathematics part here, when you integrate this d by dt s plus I plus r equal to 0, you get this capital N equal to this s plus I plus r. So this is just a simple mathematics if you integrate. Yeah. Okay. So the model consists of these three couple nonlinear ODE, which is given by this form here, and ds by dt, which is a negative alpha si. As you know that why it's negative, you know when it's negative, because it started from a constant number, population is a constant. Then when people get infected, so there will be a rate of decrease. The number of people will get the disease, okay, will get infected. So that's why there's a the in terms of the rate will be a negative part, because it's there's those who got it will of course will actually going down because of the rate infections, because those who are being infected, automatically the graph will from the top going going to down. See, I mean, in other words, so you start with the maximum, then you use up the I mean the virus actually infected some fraction of people, so the population will go down. In other words, actually those people who get infected um, will infect will go here in this category number 2, which is alpha Si, okay, and then minus the recovery part here, okay. So in other words, those who are infected, it consists of those people who are going to be um, uh, it's a mix, huh? Those people so infected with the total going to be recovered soon. So you know that in first wave pandemic, it is around 14 days for one person to recover. Okay, so we have to choose this particular beta such that it will the model will be correct. Okay, So the number 3 is the number of the recovery, the rate of recovery, beta I, okay, where those already infected and they are already recovered. Okay, so it gives a positive. Okay. So beta is represent recoveries, alpha represent rate of infection or contact per infected per day. 1 over beta represent days to recover, and alpha over beta represent R naught. R naught is the basic reproduction number. So contact per is represent contacts per infections. I will discuss more on that later. So I didn't go to these details of how to derive the solutions, but using the Euler method, EULER, um, we have this as the general form of solutions for the substitutable and the capital I and the which is the infectives and the recover or the remove, we call it. Okay, this is the standard deterministic solutions using Euler methods. Okay, actually there's another solutions for SR epidemic model, which is stochastic model. The stochastic solution. Stochastic solution, they use this random, okay, which is a bit more complicated. So we are more using these deterministic solutions. So we want to get the exact outputs uh, from the input parameters. Okay. So as I mentioned earlier, the R naught for the COVID-19 is usually, because we don't know actually. This is the first time COVID-19 evolved in China, and then in China there's um, the modelers Huang and their groups actually predicted that the rate of infection, the R naught, okay, which is alpha, the rate of infection divided by the rate of recoveries, okay. So it's around between 0.3 to 8.213. Okay, that is because this is the case they taken in Wuhan, China. Okay, so we're going to use that later for our baseline. Okay, so if R naught is greater than 1, each person on average will infect more than one person. Okay, that's the meaning of the basic reproduction number. Okay, so thus the disease will spread. So if R naught is 1, then each person will infect exactly one other person on average. Therefore, it will move throughout the population but remain constant. And if R naught is less than 1, for example, like 0.3 here, the disease will slowly going down and finally dies out. Okay. Okay. So with that, we will use this information from the previous to model our to predict the outcome. So during the first wave, it took 14 days to recover from the virus on average. Therefore, we take the rate of recovery, beta is 0.07. Okay, it's actually 1 over 14. Is it correct? Yeah. So for poor population of small size like Brunei, of nearly 500,000, we assume the infection rate for this data is selected as alpha 0.3. Actually, we also don't know because we take the data from the Wuhan reproduction number. Wuhan, they recorded the basic reproduction number is 4.3. So we multiply the R naught by beta to get 0.3 alpha. Okay, so if we do that, we our prediction is without any prevention, the model will have maximum around 2003 616 people in Brunei will get infected if there's no prevention. That is our prediction. That is around 44.3% of the total population. Okay, so as you can see here, this is the blue color here is the susceptible. So it start from the top and going down, and this the red color is the infected, and this is the recovered uh, people who already recovered. Okay, so this is the prediction. So for the social distancing, um, we take one paper also published in 2020 because this is all during COVID-19. Um, According to the research, if the risk of being infected while keeping a distance of 1 meter, it's about 13%, according to these researchers. Okay, so we take that 13% to be alpha equal to 0.13. And from figure 2, using SIR model, is predicted that if we keep on, so if we keep on taking this practicing of social distancing until, I mean, we take this social distancing as a practice. So after our predicted model will says that it will reach 0%, okay, after 260 days. Okay, so as you can see, this infected will dies out, the red color. Okay, so the next one, the Brunei government have taken quick step and action after receiving the news about the spread of the virus by imposing strict rules and regulations. Everything, schools closed, uh, working at home, working from home, and then even flight, restricted, movement control order, and so on, all this curfew and everything. So figure 3 shows that when they impose these rules or regulation as soon as possible, people get away. Because in Brunei, the beauty in Brunei is, in Brunei we have a very good high communication, IT. Yeah, people listen to the radio all the time. How many cases being recorded, uh, and people are aware. Uh, and so, in other words, with the people in Brunei support the government initiatives. So we can see that the model, the blue color, it keep on increasing, but when these rules and regulation has been imposed, these cases are overestimated in the at certain time, but it getting slowly decrease. It getting flattened, getting constant, because the government already imposed these rules and regulations so that um, we people are not moving around or gather in a big gathering and so on. See, police are going around and check and everything. So this is where the model start to fail. See, so we can actually really predict the um, the situation because of these prevention case imposed by the governments. So and then they will start the rules and regulation is being imposed, SOP being imposed, everything, MCO and so on, from March 6, 2020 until November, because November they are getting easy down now, but we look into we recorded this number of cases, the real cases. So after 260 days, it's flattened already. Okay, the red color. But the model is still increase, but at some point it's getting a constant. But again, what does it shows? It shows that by comparing the overall predicted case and real case scenarios, we the result shows that estimating parameter such as the rate of infection alpha is a difficult task because we don't know what to put here in this case alpha, because even um, if we try with different alphas due to these strict laws, social distancing, everything in place, the initial prediction will be far from reality. That is the main challenges. Okay. So for the just want to say something about the R naught. For the R naught, the basic reproduction number, as I said earlier, we take the alpha 0.13. Why 0.13? Because when the government stated that we should have uh, imposed the social distancing in the first place, okay? When you go out, you try to distance yourself with others. So we take that alpha 0.13 and divided by this beta is the rate of these recoveries, the 14 days because of the first wave. It's around 1.857. Then we found that after the second month, the R naught decreased until it become less than 1. So that is around 260 days, something like that, okay? So the graph is drastically flattened for real case scenario because of this, because of the impose of rules and regulations. So in other words, um, again, as I mentioned, even we have the reproduction number in place, we still can't actually really predict when the exact um, when the R naught is exactly less than 1, because in the real case it's already flattened in the first month, it's already getting slowly to be constant. So it means to say there will be no more new cases, new COVID cases. Okay. So the conclusion now is that we use this SIR model for looking into this prediction of the first wave COVID-19 pandemic. From the finding of using SIR model for social distancing, the value of R naught of Brunei during the first month is 1.86, because as I said earlier, the government started people who go out to keep a distance between each other. So after 1 month, the value of R naught decrease until the value become less than 1. So the trend does not show any virus spread. So again, the graph is drastically flattened for real case scenario due to Brunei government state rules and regulations in order to prevent spread of the virus. So from our conclusion, since Brunei government start to impose immediate strict rules and regulation on day one, after getting the first victim, so it will be non-viable to compare the total real cases up to 1 month. because if you see the graph earlier, after 1 month, there's no way that we can actually look into the compare with the total predicted case, because the total predicted case will still rising up compared to the real case. Because the real case is already getting flattened. So it means to say that it's going to be very hard for our model for us to estimate the parameters, especially the rate of infection, okay, alpha. So we conclude that additional factors such as variation in government strict rules, because the government keep on changing or imposing more rules and regulation to bring down the case, or to stop from the virus to spread. So SOP and so on, MCO, um, as well as the social network structure and such as social distancing. And they have some effect in terms of estimating COVID-19 duration and the number of infected cases. So my further research study is, it will be interesting if we can find out if any other complemental epidemic models such as SEIS. SEIS mean susceptible, exposed, infected, and again susceptible. There's quite a lot of epidemic model, but uh, not sure whether this model going to work or not, because it's very interesting if we want to know more about this. SEIR, another one, susceptible, exposed, infected, and recovery. And this is a more complicated one, which is published in Nature. This is even more, 1, 2, 3, see that susceptible, infected, diagnosed, ailing, mean very sick, recognize, threaten, those who ill, and extinct. This is more complicated compartment model. Okay, so it will be interesting if we want to know if they have this model, if whether they have certain effects on the prediction or improvement with the intervention of government strict rules and regulation, because uh, action is louder than words, that I call it, because with the government intervention, things can change. Okay, all right. Thank you. I think that's all I'm going to say. Thank you very much.
So, okay, thank you very much, Dr. Saiful. So, we open the floor. Any question from our colleague? Any question? Yeah, if you have question, you may unmute and you may raise any issue or any question lah.
Or you can have chat also.
Yeah, we can chat also.
Hello, good afternoon.
Good afternoon.
Yeah, I'm Dr. Jekyll. Um, I'm interested to know about more about the solution, like what the method used to obtain the solution and what tools uh, used to find the solution.
Oh,
Thank you.
okay. Thank you, Dr. Jekyll. As I mentioned earlier, we use this Euler's method. You know that this Euler method is um, it's used. We call it a recurrence how do you say this? If you know Newton-Raphson method, uh,
Iterative.
iterative method. So
Okay.
this
Okay.
is the way we use iterative method. So this is actually um, that we cannot use this manually. We have to use programming to run this because it's going to just it depends on the time step as well. Because the time step you're talking about delta t. So how many is it in terms of hour, time, day? Okay. So that's the thing that we use. I mean, there's a lot of standard textbook of how to actually derive this, the solutions. Um, if you go to these deterministic models for the SIR epidemic, yeah. I hope it answer your questions.
How about the tool
The tools, you mean?
software?
Oh, software. It depends on how you're going to use. Um, I'm not sure how what our students did it, but I think he did it using probably MATLAB or Mathematica. I'm not sure.
Oh, I see. Okay.
Yeah, yeah, it's a mathematical software, so you can use any software you want. Yeah,
Okay. Okay. All right. Thank you.
yeah.
Yeah, thank you very much, Dr. Jacob. So is there any question? Maybe question from our UBD colleague. We have Dr. Haziq here, Dr. Wiping, Dr. Albina, kan? Yeah, Dr. Saiful, I have one question.
Okay.
So, how do we, measure the accuracy of the model lah? Let's say the model we use for 1 year. So, in your opinion, the model is accurately most maybe within how many days? Do you taking that into consideration during your
Yes.
proposing the model?
Uh, Good question. But of course, as I said, in 1 month we already the the problem start arising. You see, because just within 1 month, the predicted case is not does not actually um you know I can say it's not the same as what the real case shows because of this government intervention. Because they start saying that okay, you need to go and stay at home, this and this. The model they don't have this kind of uh structure in the model. I mean, you see, if
Yeah.
you don't want to get sick, you just stay at home. That's a problem. But if you want to go out, I mean, of course, obviously people will get sick. So the model they don't have that. Of course, that the one which told you about this the CDAT model, the nature, the
Okay.
one nature and medicine. That one
Okay.
is more realistic. They even consider people going out, and they also want. But again, I when I read the papers, he doesn't stay saying that how much intervention the government, how much government have been actually imposed because it's very hard to manage in a large population. That's why we actually just focus on a small population size. But even in small population size, as I said, again, still we have a problem where this rate of infection is very hard to predict. What alpha need to be put in? We don't know yet. So because even we put certain different alpha, it will still not really actually the same. It actually doesn't actually show any resemblance. if you look into the presentation that I have, the predicted case versus the real case, just 1 month, it doesn't show any improvement. Yeah.
Okay, so is there any question? Okay, is there any more question? Okay, thank you very much, Dr. Saiful.
Thank